Hello and welcome to the Maths 2 component of the online BSc program on data science. In this video, we are going to talk about what is a linear mapping. So, let us start with an example. So, we have a grocery shop, a usual kirana shop that you go to, and let us say it is in the town of Malgudi. The shop is shop A, and we have three items that we are interested in. Rice, dal and oil, and the prices in these in shop A of these items are 45 rupees per kg for rice, 125 rupees per kg for dal, and 150 rupees per liter for oil. So, if you want to compute, for example, the cost of 1 kg of rice, 2 kg of dal and 1 kg of oil, then what do? We multiply 1 by 45, 2 by 125, 1 by 150 and we add them, and if you do that you will hopefully get 445 if I have done this computation correctly. Similarly, if you want to calculate the cost of 2 kgs of rice, 1 kg of dal and 2 liters of oil, both of these should be liters, then that is given by multiplying 45 by 2, 125 by 1, 150 by 2 and adding all those, which if I have done it correctly should give us 515 rupees. So, in general, if you have x1 kgs of rice, x2 kgs of dal and x3 liters of oil, not kgs, then how do we do that? We have to multiply 45 by x1, we have to multiply 125 by x2 and 150 by x3, and then we add up those terms. So, usually we write it in the opposite way, we write it as 45 x1 plus 125 x2 plus 150 x3. So, this is, notice, a linear combination of x1, x2, x3 with coefficients 45, 125 and 150. So, the point is, if you want to get the cost of a certain number of items and you know the cost of each individual item, then the total cost is a linear combination of the amounts of the items that you want to buy. So, we have seen this kind of idea before also, this is not the first time we are seeing it in this course, but I wanted to remind you of this. Okay. So, let us quickly summarize this in terms of what is an expression and what is a linear combination. So, the term 45 x1 plus 125 x2 plus 150 x3 is an expression. I want to explicitly say this because sometimes there is a confusion about what is an expression and what is an equation. So, this is not an equation, this is an expression. Okay. So, we can equivalently think of this as a function, and that is what this video is going to be about. We can think of this as a function CA, C for cost, A for the shop A, from R3 to R. Since for every value of x1, x2, x3 we get a real number, right. How do we do that? Because if you plug in some values for x1, x2, x3 you can evaluate. That is exactly what we did in the previous slide, where we evaluated this with specific values of x1, x2, x3, right. So, that means this is a function given a particular triple, meaning given values of x1, x2, x3, it will give us a real number. Okay. So, we can treat this as a function from R3 to R. So, since CA is a linear combination of these three variables x1, x2, x3 and with coefficients as we noted 45, 125 and 150, this is an example of a linear function. Why linear? Because it has something to do with a line, which we may study which you may have seen already in maths 1 and which we will anyway refresh after some time. But in our context it is linear because there are no powers involved here or no exponents. Yeah, it is just 45 times x1 plus 125 times x2 plus 150 times x3. Yeah, there are no other terms where you have other powers of xi's coming in, or you have some other kinds of functions, logarithm and so on. Okay, that is why it is a linear, we call it a linear function, and we will explicitly say what we mean by linear function in a little while. That is what this video is about linear mappings. Okay. So, recall we have done this before, that linear combinations can also be expressed in terms of matrix multiplication, and this is what we have done all of maybe a week back or 2 weeks ago, where we studied in great detail matrices and how they operate, and various kinds of manipulations. So, it is important to remember this, because we are going to use this soon for various other purposes. So, we can express the function C A, which was defined as a linear combination 45 x 1 plus 125 x 2 plus 150 x 3 as the matrix multiplication, where we have the coefficients as a row matrix 45, 125, 150, and the variables x 1, x 2, x 3 as a column. We have seen this before. I just want you to remember this for what is coming next. Okay. So, I again want to reiterate. Remember that this is, you can think of this either as a linear combination. When I say this, I mean this term 45 x 1 plus 125 x 2 plus 150 x 3 as a linear combination, or an expression. It is not an equation. Okay. An equation is when you equate it to something and then we will try to solve. Yeah. So, an equation is when you have an equal sign somewhere and you say this expression is equal to some other expression. Okay. That's when we will say it is an equation. Okay. So, let us go on. So, let us talk about cost linearity. Okay. So, this is what was hidden in that statement about it being a linear function. So, caterer gets an order from office 1 in Malgudi on Monday for 30 tiffins prepared in some prescribed way. Maybe they want just rice and dal prepared separately and with more oil. Okay. So, for office 1 they want 30 tiffins. So, the caterer estimates that they will need 20 kgs of rice, 10 kgs of dal and 4 liters of oil, and they go to shop A to buy these. Okay, this is for office 1 in Malgudi. So, on Tuesday they get an order from office 2, so which is a different office from office 1, and they want a different way of preparation. Okay, they want less oil, but maybe they want the rice to be more fluffy or less fluffy or something, and for whatever purpose, whatever way in which they want it to be made, the caterer estimates that for 40 tiffins they will need 40 kgs of rice, 12 kgs of dal and 2 liters of oil, less oil. Okay. So, the office 2 is health conscious. Okay. And then they go to shop A for buying this material. Okay. On Wednesday they get orders from both offices, office 1 and office 2. Office 1 wants 15 tiffins, office 2 wants 50 tiffins. Maybe office 1 did not like so much, some people in office 1 did not like how they prepared it, so only half of them ordered, but they still wanted to be prepared in their way, whatever that was, and office 2 wants it to be prepared in their way, whatever that was. Okay. So, the question is, how much does the caterer spend at shop A? Okay, what is the cost to the caterer, or how much does shop A earn from the caterer? Okay. Now, the natural way of doing this, I mean one way of doing this maybe, is to ask, well, for 50 tiffins for office 1, I know how much was required for 30 tiffins for office 1. So, 15 tiffins will require half of that amount, right. So, 10 kgs of rice, 5 kgs of dal and 2 liters of oil, and 50 tiffins for office 2 will require 5 by 4 times whatever was used up on Tuesday, because that time they had offered 40 tiffins. So, you would have 5 by 4 times 30, 5 by 4 times 12 and 5 by 4 times 2 respectively kgs and liters of rice, dal and oil. Okay. So, this is what we are noting here. On Wednesday for office 1 we will require 10 kgs of rice, 5 kgs of dal and 2 liters of oil. On Wednesday for office 2, which remember has 50 tiffins, we will require 5 by 4 times the amounts on Tuesday, which means you need 37.5 kgs of rice. Earlier it was 30 kgs of rice on Tuesday for 40 tiffins, 15 kgs of dal. So, I think we had 12 kgs of dal on Tuesday, and 2.5 liters of oil. We had 2 liters of oil on Tuesday. Okay, so, we know for each office how much rice, dal and oil is going to be required. So, the caterer will go to shop A and will buy the sum of these two. So, the total required quantities of rice, dal and oil on Wednesday will be 47.5 kgs of rice, 20 kgs of dal and 4.5 liters of oil. So, I am just adding up whatever we need for office 1 on Wednesday to whatever we need for office 2 on Wednesday. Okay. So, the cost to the caterer at shop A, they always buy from shop A, this is what we know, is 45 times 47.5. So, you substitute plus 125 times 115 plus 150 times 2.5. So, you substitute these values 47.5, 20 and 4.5 in our linear combination or in the cost function CA. You evaluate the cost function at 47.5, 20, 4.5, right. So, that gives us 5312.5. This is something you have to calculate, and if I have done my calculation right, hopefully this is what you will get. Okay. So, now we could calculate this a bit differently. How do I do that? So, we can calculate what was the cost to the caterer on Monday for office 1. So, how do I do that? Well, on Monday how much was bought? On Monday we had I think 20 kgs of rice, 15 kgs of dal and 10 kgs of dal and 4 liters of oil. So, you put in this vector in R3 20, 10, 4, you put it into the cost function CA, or you evaluate the linear combination with x1 equals 20, x2 equals 10 and x3 equals 4, and then you get 2750 rupees. That is for office 1 on Monday. On Tuesday we had 40 tiffins for office 2, and for that we had I think 30 kgs of rice, 12 kgs of dal and 2 liters of oil. So, you take this vector 30, 12, 2 and evaluate the cost function on this vector or this element of R3, or equivalently you put it into the linear combination, and what we get is 3150 rupees. Okay. So, what have I done? I have computed the costs on Tuesday and Monday. Okay. So, now I am claiming that the cost to the caterer on Wednesday is half times 2750 plus 5 by 4 times 3150, which is 5312.5. So, the claim is that both of these are the same, that is basically what I want to say. Now, why is that happening? We will see that. So, the first method can be summarized as calculating the vector for Wednesday by adding half times the vector for Monday. By the vector I mean the demand vector, the amounts of quantity that are required. So, the demands on Monday, you took half of that plus 5 by 4 times the demands on Tuesday. That is exactly how we got these numbers. So, these numbers 47.5, 15 and 2.5, that is exactly how we got those numbers, right. And then we compute the cost function on those numbers. That is how we did the first method. The second method can be summarized as adding half times the cost for Monday and 5 by 4 times the cost for on Tuesday. Okay, so I will summarize this in this table. So, these are the quantities of rice, dal and oil that we require on Monday, Tuesday and Wednesday respectively, and we see that the third column, the third row is obtained as half times the first row plus 5 by 4 times the second row, right. And this is where linearity is coming in. Okay, so now I've converted whatever I've done before to a sort of vector problem. Okay, so let's now understand why does the second method work. So for the second method, what did we do? So I want the cost on Wednesday, total cost on Wednesday, right, which we know is certainly given by the evaluating. So 45 times rice required on Wednesday plus 125 times dal required on Wednesday plus 150 times oil required on Wednesday. Right. But how much rice was required on Wednesday? Well, we just saw that is half times the rice on Monday plus 5 by 4 times the rice on Tuesday, and we can do the same thing for dal and oil. So this is half times the dal required on Monday plus 5 by 4 times the dal required on Tuesday plus 150 times half times oil on Monday plus 5 by 4 times the oil on Tuesday. Okay, now we can separate out the quantities for Monday and Tuesday. So if we do that, we get so I will do it in one step. Ideally I should have written one more step, but I think you can follow what's happening. So this is half times 45 times rice on Monday plus the bracket here plus 125 times I don't need to put the brackets by Bodmas, but I am anyway, just to be careful, dal on Monday plus 150 times oil on Monday. Okay, these are all the terms for Monday, and then plus 5 by 4 times 45 times rice on Tuesday, the same expression, but now for the Tuesday quantities, 125 times dal on Tuesday plus 150 times oil on Tuesday, right. But now whatever we have inside the curly brackets is exactly evaluating the linear combination that I have on the quantities for Monday and Tuesday respectively. Yeah. So this is exactly whatever we have in the curly brackets is exactly the cost on Monday, that is the first curly bracket, and whatever we have in the second curly brackets is the cost on Tuesday. Yeah, and this explains why the second method works. Okay, the first method is clearly the sort of long way of doing it and the neat way of doing it, but the second method is clearly much shorter and yields the same answer, I mean, which otherwise we wouldn't have discussed it, and this is the reason why. So what really worked here? Why did this work? What worked here was the fact that we had a linear combination. Yeah, so that's why this function is, I said this function is linear, because these terms can split up. You can break them into two, and we will make this more explicit as we go on. Okay, so but I hope I've convinced you that both the methods give you the same answer.